Okay. So yesterday we discussed about UV visible spectroscopy, the electronic transitions. We discussed electronic transitions. We discussed the principle behind UV visible spectroscopy. Okay. Now today we'll discuss few terms involved in UV visible spectroscopy, and then we'll discuss selection rule for UV visible spectroscopy and applications of UV visible spectroscopy, qualitative analysis and quantitative analysis, or qualitative and quantitative applications of UV visible spectroscopy. Okay. Chromophores, the first term used in UV visible spectroscopy. This chromophores, chromophores. Okay. The part of a molecule, what are chromophores? The part of a molecule responsible for imparting color, they give color, are called as chromophores. They give color to the molecule. Because of them, the molecules, they get their specific colors. Okay. Or the functional groups containing multiple bonds, the functional groups containing multiple bonds capable of absorbing radiations above 200 nanometer due to non-bonding pi star or pi to pi star transitions. They are capable of absorbing radiations above 200 nanometers in ultraviolet region. Okay. Above 200 region, above 200. Okay. Due to non-bonding to pi star transition and pi to pi star transitions. Pi to pi star transitions. For example, these are chromophores. This carbon oxygen double bond, carbon nitrogen double bond, carbon nitrogen triple bond, carbon carbon double bond, carbon sulfur double bond. Okay. So these are all are capable of absorbing radiation above 200 nanometers due to non-bonding to pi star transitions. The electrons from non-bonding orbital, they get excited to pi star orbitals, or from pi orbital to pi star orbitals, they get excited. Okay. These molecules are capable of absorbing this UV radiation above 200 nanometers. Okay. So they are known as chromophores. They are known as chromophores. Okay. To interpret UV visible spectrum, following points should be noted. Following points should be noted. Non-conjugated alkenes show an intense absorption below 200 nanometers. Non-conjugated alkenes, they show an intense absorption below 200 nanometers. This is absorption. This is lambda max. Okay. Absorption below 200 nanometers. Below 200. Just below 200 nanometer. Okay. Therefore, and are therefore inaccessible to UV spectrophotometer. Inaccessible to UV spectrophotometer. Non-conjugated carbonyl group compounds, non-conjugated carbonyl group compound give a weak absorption band in the 200 to 300 nanometer region. This 200 to 300 nanometer. Here they give absorption peak. Okay. This is, see, this is example of chromophore. This group you see here. Okay. For example, acetone, which has lambda maximum 279 nanometer. The lambda maximum is 279 nanometer. And cyclohexane, this is simply a cyclohexane. The lambda maximum is 291 nanometer. This is, let's see here. This is cyclohexanone, not cyclohexane. Cyclohexanone. Cyclohexanone. It is cyclohexanone. Okay. lambda maximum is 291 nanometer. When double bonds are conjugated, in a compound, lambda maximum is shifted to longer wavelength, For example, 1,5-hexadiene has lambda maximum 178 nanometer. This 1,5-hexadiene has lambda maximum 178 nanometer, whereas 2,4-hexadiene has lambda maximum 227 nanometer. 227 nanometer because of conjugation. Lambda maximum has shifted to longer wavelength. Understood? See, conjugation of carbon-carbon double bond and carbonyl group shifts the lambda maximum of both groups to longer wavelengths. It gets shifted to longer wavelength. Okay. For example, we can see here also ethylene has lambda maximum 171 nanometer. Ethylene, the lambda maximum is 171 nanometer, and acetone has lambda maximum 279 nanometer. The same, if we incorporate a carboxylic group in this, okay, the acetone, the lambda maximum gets shifted to longer wavelength, 279 nanometer. 279 nanometer. Okay. Now, auxochromes. The functional group attached to a chromophore. Which modifies the ability of the chromophore. To absorb light. So what it does, it modifies the ability of the chromophore to absorb light, altering the wavelength or intensity of absorption. Or the functional group with non-bonding electrons that does not absorb radiation in near UV region, but when attached to a chromophore, alters the wavelength and intensity of absorption. Okay, so this one is easier to remember. The functional groups attached to a chromophore, which modifies the ability of the chromophore to absorb light, altering the wavelength or intensity of absorption. It changes its ability to absorb. Okay, we'll see how. See, for example, benzene, lambda maximum 255 nanometer. Lambda maximum 255 nanometer. Phenol, lambda maximum 270 nanometer. This is auxochrome. It has shifted its wavelength to 270 nanometer to longer wavelength. It has this auxochrome has shifted the ability to absorb, the ability of benzene to absorb to longer wavelength. Okay. Similarly, aniline. This is our auxochrome. Okay. Auxochrome. Okay. This part, it is attached with this benzene. So this, its ability to absorb, the ability of benzene to absorb is changed. So this it absorbs at longer wavelength. It absorbs at longer wavelength. It absorbs at longer wavelength. Okay. So these are auxochromes. Auxochromes, they change the ability of a compound to absorb. Okay. Maybe to longer wavelength or to shorter wavelength. Both ways they can change. Okay. Okay. Absorption and intensity shifts. The next topic, absorption and intensity shifts. Now, these are also important topics. Bathochromic shift or red shift, hypsochromic shift or blue shift, hyperchromic effect, and hypochromic effect. Hyper or hypo. Hyper or hypo. Suppose this is lambda maximum, this is absorption. Okay. So this is, if it shifts here, this is, we call blue shift, red shift, and if this amplitude increases, it is known as hyperchromic effect, and if the amplitude decreases, it is known as hypochromic effect. It is known as hypochromic effect. Hypochromic effect. Okay, see here. We'll see. Okay. When absorption maxima, lambda max, suppose this is lambda maximum, lambda. When absorption maxima of a compound shifts to longer wavelength, So this is, if it shifts here to increasing wavelength. When absorption maximum, lambda maximum of a compound shifts to longer wavelength, it is known as bathochromic shift or red shift. It is known as red shift. Okay, it is known as red shift. When absorption maxima, suppose this the compound A, and if there is a modifier, an exochrome or an auxochrome. Okay, when absorption maxima of a compound, if the absorption maxima of this compound, suppose initially it is here, and if it shifts to longer wavelength, it is known as bathochromic shift or red shift. It is known as red shift. It is known as red shift. Okay, it is known as red shift. Okay. Now, the effect is due to presence of an auxochrome, as I told you. The effect is due to presence of an auxochrome or by the change of solvent. There may be a change of the solvent, or there may be an addition of an auxochrome. Because of this, there is a shift in its ability to absorb ultraviolet radiation. Okay. For example, an exochrome group like OH or this oxymethyl or hydroxyl causes absorption of compound at longer wavelength. Absorption of compound at longer wavelength. We'll see here. Okay. In alkaline medium, we'll discuss some examples. In alkaline medium, paranitrophenol. In alkaline medium, paranitrophenol shows red shift. It shows red shift because negatively charged oxygen delocalizes. Negatively charged, it gets delocalized. Okay, because negatively charged oxygen delocalizes more effectively than the unshared pair of electrons. Okay, I'll clear it. Okay, you can see in the alkaline medium. Okay, in alkaline medium, paranitrophenol shows red shift. So paranitrophenol 255 nanometer, but in alkaline medium, it is lambda maximum shifts to red shift, longer wavelength, that is bathochromic shift or red shift. The lambda maximum becomes 265 nanometer. Okay. Now, when absorption maxima, hypsochromic shift, the other one. Okay. Okay. When absorption maximum, lambda maximum, okay, of a compound shifts to shorter wavelength, here, left side, shorter wavelength, it is known as hypsochromic shift or blue shift. It is known as hypsochromic shift or blue shift. Hypsochromic shift or blue shift. Understood? The effect is due to presence of an group which causes removal of conjugation, because it may be because of the removal of the conjugation from the molecule, or by the change of solvent, or there may be a change in the solvent. Okay, we'll discuss few examples. Okay, now the same thing, aniline. Aniline shows blue shift in acidic medium. Blue shift in acidic medium, it loses conjugation. Here, let's see here, this, in this there is conjugation, so lambda maximum is 280 nanometer. There is conjugation, this, okay, there is conjugation. It can, so this electrons are this pi electrons, they are degenerate electrons, okay, there because of conjugation. Aniline shows blue shift in acidic medium, it loses conjugation. But in acidic medium, here in acidic medium, the conjugation is lost. Because of loss of conjugation, lambda maximum becomes 265 nanometer. So there is decrease, it shifts, it decreases, lambda maximum decreases, okay. So it shifts to left side, or we call it hypsochromic shift. Hypsochromic shift or blue shift. Hypsochromic shift, or suppose for aniline, lambda maximum is here. Lambda maximum, it is 280 nanometer, 280 nanometer, lambda maximum. But if we change the solvent in acidic medium, the same molecule absorbs here 265. So it is shifting, it is decreasing, okay. So it is shifting to left side, which is blue shift. We call it blue shift or hypsochromic shift. Hypsochromic shift. Understood? There is loss of conjugation and there is change of the solvent also. Now, hyperchromic shift, hyperchromic effect, hyperchromic effect, hyperchromic effect, hyperchromic effect. This is absorption and this is the wavelength, okay. This is the amplitude, okay. This is our amplitude. Oh, no. When absorption intensity, this molar efficient coefficient, this is absorption intensity. When absorption intensity of a compound is increased, this is increased, okay, amplitude increase, it is known as hyperchromic shift. Hyperchromic, see, this increases, so this is known as hyperchromic shift. Hyperchromic shift. If you can see here, if auxochrome introduces to the compound, the intensity of absorption increases. Auxochrome, because of the introduction of an auxochrome, the intensity of absorption increases. See here, this is pyridine, lambda maximum is 257 nanometer, lambda maximum will remain, okay. But because of this introduction of this auxochrome, 2-methylpyridine, lambda maximum 260 nanometer, but the intensity also increases. The intensity also increases. Intensity also increases, okay. It is not shown here. Intensity also increases, okay. See, hypochromic effect. Now, hypochromic effect. When absorption intensity, this is absorption intensity and this is lambda maximum, okay, lambda wavelength, okay. When absorption intensity of a compound is decreased, suppose it is decreased, suppose initially it was here, but now it decreases, it decreases. Okay, when absorption intensity of a compound is decreased, it is known as hypochromic shift. Hypochromic shift. See here, this is epsilon is 19,000 for naphthalene. Epsilon is 19,000. Absorption intensity is 19,000, but because of the introduction of this Auxochrome, 2-methyl naphthalene, this becomes 2-methyl naphthalene. This intensity decreases 10,250. Absorption molar coefficient, molar extinction coefficient becomes 10,250. So it is decreasing. The intensity is decreasing. Okay, so it is known as hypochromic shift. It is known as hypochromic shift. Understood? Hypochromic shift. We can see here, down hypochromic shift, up hyperchromic shift, to left side blue shift, or to right side right or longer wavelength. Towards longer wavelength we call it red shift, and towards shorter wavelength we call it blue shift. Okay, bathochromic shift, hypsochromic shift, hypochromic shift, hypochromic shift. Okay, now applications of UV visible spectroscopy. Applications of UV visible spectroscopy. Okay, so applications of UV visible spectroscopy in analytics or analytical chemistry. There are 5 main regions to measure UV visible spectra of a compound. You see here, UV visible spectroscopy allow components present in the sample solution to be identified. We can identify the compounds present in a solution or in a sample. More precisely, the position and to some extent the profile of absorption peaks allow specific compounds to be identified. Specific compounds to be identified. Because of this absorption peaks, we can identify the specific compounds. Okay, for example, organic compounds can be identified by their spectra, or solvent purity can be easily checked by UV visible spectroscopy. Okay, we can identify any organic compound using this UV visible spectra. Absorption peaks can be used to quantify. See here, absorption peaks can be used to quantify the investigated sample. For example, the sample concentration can be calculated from the absorbance value of the peak. Absorbance value of the peak. For example, the sample concentration can be calculated. Okay. All the drawings. Mute yourself. 467. Roll number 467. Okay. Now, few more things. Based on relationship between absorbance and sample concentration. Absorbance and sample concentration. This is absorbance and this is lambda. So based on relationship between absorbance and sample concentration, UV visible spectroscopy is applied as a quantitative analytical techniques in market segments such as, for example, water testing, food and beverages, pharmaceuticals, chemical and biotech industry. Everywhere, all these industries, they apply these technique. Okay, the position of the peaks in the spectrum reveals information about the molecular structure of the sample. For example, specific functional groups of a molecular structure, specific functional groups of a molecular structure, such as carbon-oxygen, carbonyl group, or carbon-carbon double bonds, absorb at specific characteristic wavelengths. They have specific characteristic wavelengths where they absorb. So we can easily identify any organic molecule. Okay. See here more. The spectrum may reveal specific physical properties of the sample molecules. For instance, from the UV visible spectrum, it is possible to calculate the extinction coefficient of the sample. This extinction coefficient, epsilon. Calculate the extinction coefficient of the sample. Calculate the melting point of proteins and nucleic acids by measuring the UV visible spectra at different temperatures. At different temperatures, we can calculate the melting point of proteins and nucleic acids. Determine the rate of a reaction by monitoring the absorption spectra as a function of time, also known as kinetic measurements. We can perform kinetic measurements, okay, to determine the rate of a chemical reaction. Okay. Finally, position and profile of the peaks in the spectrum can give information about the microscopic environment of the sample molecules. Microscopic environment of the sample molecules. For example, the presence of impurities or other solvents in the sample, the presence of impurities or other solvents in the sample solution has an effect on position and of the profile of the peaks. So it can change the position and the profile of the peak. In other words, the peaks may be broader or have shifted due to impurities. There may be bathochromic shift or hypsochromic shift, hyperchromic shift or hypochromic shift. Okay, so the peaks, they can change, or they may be sharp, or they may become broader. Understood? They may become broader. Hello.